Hello, welcome to another module in this massive open online course on the principles of 3G, 4G wireless communication systems. In the previous module, we have looked at a basic introduction to MIMO systems, a simple model of the MIMO system, all the transmit vector, the receive vector and the MIMO channel matrix. Let us look at a simple example to understand this better. So, let us look at a simple example of a MIMO system. We will consider a MIMO system with R equal to 3 receive antennas and T equal to 2 transmit antennas. So, in effect this is a 3 cross 2 MIMO system. We refer to the MIMO system as an R cross T MIMO system. Since R equal to 3, T equal to 2, this is a 3 cross 2 MIMO system. Naturally, the transmit vector is equals x1 comma x2. x1 is the symbol transmitted on the first transmit antenna, x2 is transmitted on the second antenna, and therefore, naturally this is a two dimensional transmit vector. What we have is we have a 3 cross 2 MIMO channel, which means we have 3 receive antennas and 2 transmit antennas. Therefore, on each transmit antenna we can transmit a symbol. So, x1 is the symbol transmitted on the first transmit antenna, x2 is the symbol transmitted on the second antenna, x1, x2 is therefore the two dimensional transmit vector which comprises of the symbols transmitted from both the transmit antennas. Since we have 3 receive antennas, my receive vector equals y1, y2, y3, where y1 is the symbol received on the first receive antenna, y2 is the symbol received on the second receive antenna, y3 is the symbol received on the third receive antenna, and therefore, we have a 3 dimensional receive symbol vector, correct. So, we have a 3 dimensional receive symbol vector, and naturally the channel matrix H is equal to R cross T. So, this is a 3 cross 2 dimensional, basically this is R cross T. So, channel matrix H is basically a 3 cross 2 matrix containing a total of 3 times 2, that is 6 channel coefficients. Therefore, I can write this system now as follows. I have the 3 dimensional received vector y1, y2, y3, which is equal to the 3 cross 2 channel matrix h11, h12, h21, h22, h31, h33 times x1, x2, which is my 2 dimensional transmit vector, plus the 3 dimensional noise vector, which is W1, W2, 3 dimensional noise vector, that is W1, W2, W3. So, this is my 3 dimensional received vector y bar, this is my 3 cross 2 matrix which is H, this is my 2 dimensional transmit vector x bar, and this is the 3 dimensional received vector or 3 dimensional noise vector w bar. And now writing each element of the received vector y, we have y1 equals h11 x1 plus h12 x2 plus w1, y2 equals h21 x1 plus h22 x2 plus w2, and we have y3 equals h31 x1 plus h32 plus h32 x2 plus w plus w3. All right. So, we have the 3 received symbols y1, y2, y3, the transmit symbols x1 and x2, and now we have these relations, or we have this model, that is y bar equals h x bar plus w bar, where y bar is the 3 dimensional receive vector, x bar is the 2 dimensional transmit vector, h is the 3 cross 2 channel matrix, w bar is the 3 dimensional noise vector, and we have also written the 3 equations for each of the received samples y1, y2, y3 to illustrate the model for the received sample in this simple example of a 3 cross 2 MIMO system. In general, when we have an R cross T MIMO system, for a general MIMO system, for a general R cross T MIMO system, I can write the symbol YL, where YL is symbol received on the nth receive antenna. I can write this as, well, I can write this as h of L1 times x1, h of L2 times x2 plus h of Lt times xt plus w of L. So, the symbol on the nth receive antenna YL can be represented as YL equals h of L comma 1 times x1 plus h of L comma 2 times x2, so on and so forth until h of L comma t times xt plus w L. So, this is the general expression for the symbol received on the nth receive antenna. Let us now look at some special cases in this MIMO system, for special cases of MIMO system. So, let us look at some special classes of special cases of these MIMO system. One is something that we are already familiar with, when t equal to 1, when the number of transmit antennas equal to 1. When the number of transmit antennas is equal to 1, we have an R cross T MIMO channel, but t equals 1. So, we have an R cross 1 MIMO channel, but R cross 1 MIMO channel is nothing but a single vector, because R cross 1 dimensional matrix is nothing but a vector of R dimensions. Therefore, the model for this MIMO system can be expressed as y1, y2 up to yr equals h1, h2 up to hr times x plus w1, w2 up to wr, and we have already seen this model. This is nothing but a model for a multiple receive antenna So, this is a model for a wireless communication system with multiple receive antennas and a single transmit antenna. We have already seen this model. We have seen this model in the context of receive diversity, and we also demonstrated that maximal ratio combining is the optimal reception technique, and this is therefore also known as a single input multiple output wireless communication system model, because we have a single transmit antenna and multiple receive antennas. This is also known as a single input. This special case is known as a single input multiple output wireless system or a CMO wireless system. So, this wireless system, which has a single transmit antenna and multiple receive antennas, is also known as a CMO or single input multiple output. This is also known as a single input. This is also known as a CMOS system. So, this is, let me write this down over here. This is also known as a CMO, SIMO system, or basically a single input multiple output wireless communication system. Let us look at now the other case when R is equal to 1, number of receive antennas is equal to 1, that is basically number of receive antennas is equal to 1 and the number of transmit antennas is arbitrary. Therefore, we have an R cross T channel matrix, but R is equal to 1. So, therefore, I have a 1 cross T channel matrix, that is, which means I have a row vector, and this is a very interesting scenario where which we have not seen before, where we have multiple transmit antennas and a single receive antenna, and therefore, I can represent this as y1 is equal to the row vector h1 h2 ht times x1 x2 xt plus w1, which is the noise sample, and this is the channel vector, and therefore, I can denote this as y1 equals h bar Hermitian x bar, where x bar is the transmit vector, plus w1, where h bar, my channel vector h bar conjugate, h bar is equal to h1 conjugate h2 conjugate ht conjugate. Therefore, you can see that h Hermitian, where I am taking the transpose and conjugate, will give me h1 h2 ht, right. So, I can represent this as y1 equals h Hermitian x bar plus w bar, where h bar is the channel vector, and this is a very interesting scenario of a single receive antenna and multiple transmit antennas, which we have not seen before. That is, this is an instance of what we call transmit diversity, because there are multiple transmit antennas, and this is also called as a multiple input, because there are multiple transmit antennas, multiple input, single output, because this is a single receive antenna. So, this is a multiple input single output wireless communication system or a MISO wireless communication system. So, this is also known, this is a MISO wireless system or multiple input this is also known as a MISO wireless communication system or a multiple input single output wireless communication system. And of course, now the most special case when R is equal to 1 and T is equal to 1, that is, you have a single transmit antenna and a single receive antenna, reduces to the standard scenario of a Rayleigh fading channel. So, when we have a single transmit antenna, R equals 1, T equals 1, right. So, we have the scenario that we have seen in the very beginning, that is y equals hx plus w. This is the fading channel coefficient. The fading channel coefficient, and this system model, this is termed as SISO, that is single output or single input single output So, when we have r equal to 1 and t equal to 1, we have back to the standard scenario, which is basically a single input, single output wireless communication system, or also known as a CISO wireless communication system. Alright. So, these are the various special cases of a MIMO system. Now, a little bit about the noise vector, because we have not said anything about the noise. The noise vector W1, the noise vector, if I look at the noise vector W1, what is this? This is my r dimensional noise vector, where each Wi is Gaussian with mean 0, variance sigma square. That is to say that expected value of Wi is equal to 0 and expected value of magnitude Wi square, which is equal to expected value of Wi into Wi conjugate is equal to sigma square. Further, we are going to assume that the different noise elements, further a standard assumption is that different noise elements, that is Wi, are IID, that is these different noise elements are independent and identically distributed, and since these are independent, as we have already seen, expected Wi Wj conjugate is equal to expected value of Wi into the expected value of Wj conjugate, which is equal to 0 if I is not equal to j. Therefore, what we have is we have expected value of Wi into Wj conjugate is equal to 0 if I is not equal to j, and expected value of Wi into Wj conjugate, if I equal to j, this becomes expected value magnitude Wi square, which is equal to sigma square, that is the variance or the power of the noise. Therefore, to combine these two results and represent it in a single statement, we say expected value of Wi into Wj conjugate is equal to sigma square if I is equal to j, 0 if I is not equal to j. So, this is independent. So, these noise samples are independent, identically distributed across the receive antennas. Okay. And the one last thing we would like to do is we would like to characterize the covariance matrix of this noise, that is W bar, expected value of W bar, W bar Hermitian which is termed as the covariance matrix of this noise, which is equal to expected value of, let me write this over here, W1, W2, WR times W1 conjugate, W2 conjugate, WR conjugate, and if I expand this, I am going to have the expected value of this W bar Hermitian is an R cross R matrix. The 1 comma 1 element is magnitude W1 square, 2 comma 2 is magnitude W2 square, so on, magnitude WR square, and here we have W1, W2 conjugate, W2, W1 conjugate, W1, W3 conjugate, W3, W1 conjugate, and so on. Now, if you look at this matrix, you can clearly see, if you look at this matrix, you can clearly see that all the diagonal elements, expected value of magnitude Wi square, expected magnitude W2 square, so on, are sigma square, while the off diagonal entries are 0, expected value of W1, W2 conjugate, W1, W3 conjugate, W3, W2, W1 conjugate, these are 0. Therefore, the expected value of this matrix is a diagonal matrix with sigma square, each element on the diagonal equal to sigma square, the rest of the entries are equal to 0, and therefore, if I bring the sigma square out, this is the diagonal matrix, which is, this is the diagonal matrix which is sigma square times identity. So, when the different noise elements are 0 mean, independent, identically distributed with variance sigma square, the noise covariance is basically sigma square times the identity matrix, which is R cross R dimensional. So, this is the R times R dimensional identity R cross R dimensional identity matrix. To understand this, let us do a simple example. Let us consider a MIMO system, again consider a MIMO system. With R equal to 3 receive antennas and the noise variance sigma square in dB equals minus 3 dB. Considering IID noise elements, what is the covariance? What is the noise covariance? Well, as we already seen before, the noise covariance R is equal to sigma square identity, where I is the R cross R, that is 3 cross 3 identity matrix. Here we are given that sigma square, the noise in dB equals minus 3 dB, which implies 10 log 10 sigma square equals minus 3, which implies sigma square equals 10 power minus 0.3, which is approximately equal to half. 3 dB is basically a factor of 2. So, minus 3 dB is a factor of half, and therefore, R equal to half, that is sigma square times 3 cross 3 identity matrix, which is basically equal to, if you look at this matrix structure, it is half, half, half on the diagonal and zeros everywhere. So, this is the covariance matrix, and what is this R? This is basically my noise covariance matrix, which is sigma square times identity. In this case, sigma square equals half. I is the 3 cross 3 identity matrix. So, this is the 3 cross 3 identity matrix, 3 cross 3 matrix with half on the diagonal and zeros everywhere else. So, with this module has introduced us to basically a simple example of a MIMO system, some special cases of MIMO systems such as SIMO systems, MISO systems, and the standard CISO system, and also we have seen the properties of the noise elements when the noise elements are independent, identically distributed across the various receive antennas. So, let us stop this module here, and we will continue with other aspects in subsequent modules. Thank you very much.